Now, I would like to introduce my colleague and friend, Professor Bernard Bercu from Toulouse University. Bernard Bercu defends his PhD on stochastic algorithm in the 19th of the last century. He works on statistics, large deviation, and stochastic algorithms. He's actually well known as the French Mahout because of his very innovative work on the elephant walk that maybe he will tell you later. He will give lectures on exponential inequality and their application in statistics. Please welcome Professor Bernard Bercu.
Thank you, Fabrice, for this introduction. Thank you very much to be here, and thank you, Fabrice, for this nice introduction. So I will make an introduction on concentration inequalities for some of independent random variables. And then I will talk also about applications. You can see well my slides. All is okay for my slides?
Yes.
Okay, perfect. So do not hesitate to stop me if you have questions, okay? So I will start. The topic of concentration inequalities is start in the last century with works of Dings, of Chernoff, of Kramer, and now you can see many papers on concentration inequalities because they are widely used in statistical learning, for example. You have a famous review, JMLR, Journal of Machine Learning Research. And in this journal, you have many papers using tools from concentration inequalities. So if you have a good background in concentration inequalities, you can make nice things on the statistical learning, machine learning, etc. So I will start with a very simple example. This is the outline of my talk. So a very simple example. How can we prove that the sum from 0 to n of the binomial number capital N k is smaller than exponential 1 times capital N divided by n all at the power n? So do you have any idea how to prove this? I am asking you a question. Can someone answer me? How you will manage to prove this?
Sir, is it by using approximate?
Is it by using Stirling approximation? No, because n and capital N are fixed. I want an inequalities which is true for all values of capital N and N. So you don't. If you use Stirling approximation, it will not work because Stirling approximation is true for n large enough. Do you have any other idea how to prove this?
Sir, I'm trying to think.
And for example, you
Sir,
yes,
if I use in summation over k from 0 to small n, n choose k, this is equal to 2 to the power capital N. So by that method, 2 to the power 2 is less than e, and from this approximation 2 to the power capital is e to the power less than e to the power capital N, and
so your idea is to say that the sum from 0 to capital N of the binomial coefficient is smaller than 2 to the power capital N. This is your idea.
yes sir, but as small n is less than capital N, hence if the total sum 0 to capital N is equal to 2 to the power capital N, hence 0 to n summation is should be less than 2 to the power capital N. But I think my idea is wrong because I am assuming 2 to the power capital N, but the power is here is small n.
Exactly. The power here is small n and is not capital N. So the right hand side here will be really small. So it's not a good idea. So numerically, how is it working? If you take capital N to be 100 and small n to be 20, the ratio capital N over small n is 5. So if you compute the left-hand side, for these two values, you have a large number here. But if you divide this large number by 5 times exponential 1 at the power 20, you will obtain 0.015. So the upper bound is not too bad. And if you use, for example, if you use, I will change just a moment. I'm trying to do something. Sorry, just a moment. I am just a moment. If I use Wolfram alpha, for example, if I compute this quantity, so the ratio is about 0.015, etc. So now, if I change the values, I replace capital N by 200, not 100, and the ratio is little n is 10. The ratio is 10. So you see that the ratio is not too bad also. So I've chosen capital N to be 200, little n to be 20, 200 over 20 is 10. So the ratio is not too bad. Is 0.03, etc. So now if I continue, but with larger values, it will not work. If I take capital N to be 1000, the capacity of my computer is not working. So numerically, for large values, I will have problem. Okay, So I go back to my talk. Okay. How can I solve this problem? You can see my slide very well. Is it okay? Yes?
Yes, sir.
Okay, so I continue now. This quantity looks like a probability that a binomial distribution.
Sir, your screen is, your slides are not visible.
My slides, so, sorry.
You were showing the directory, Bernard. Yeah, now it's visible.
It's visible, okay. So this sum on the left-hand side looks like the probability that a binomial distribution with parameter capital N and 1/2 is smaller than small n. Okay? So let's denote by Sn a random variable with binomial capital N and a half distribution. The probability that Sn is smaller than small n is 1/2 to the power n, the sum from 0 to n of the binomial coefficient. So if I multiply by 2 to the power n, my left-hand side, my sum, is smaller than 2 at the power capital N times the probability that a binomial distribution is smaller than n. So I am thinking that I can use probability to solve this problem, to solve the previous problem. Okay. So let's do it. I want to evaluate the probability that a binomial distribution is smaller than n. However, I cannot directly use Markov inequality because the Markov inequality says that for any positive random variable x, the probability that x is greater than a, not smaller than n, but greater than a, is smaller than the mean of x divided by a. So my second question is it possible in that setting to use Markov inequality to evaluate the probability that Sn is smaller than n? What do you think about that? What do you think about that? Second question. Is it possible to evaluate the probability that Sn is smaller than little n using Markov inequality?
Yes, sir. It can possible.
How you will do it?
Sir, probability x greater than equal to a is less than equal to like probability Sn less than equal to n is
I don't think it's possible because in the equality, it's given that the binomial distribution is less than n, whereas in the Markov inequality, the signs are different. So I cannot show that the binomial distribution is less than n is less than some certain quantity that would be something like expectation of 1 by a. So I don't think Markov inequality will be applicable here.
Yes, you're right. A direct use of Markov inequality is not possible here. But if you multiply Sn by a negative quantity, let's say t, if you multiply Sn by t, where t is negative, you will change the sign of the inequality. And we will do it right now. So imagine that t is a negative real number. So probability that Sn is smaller than n, if you multiply by t, this is equal to the probability that t times Sn is greater than nt. Is it okay?
Yes, sir.
Okay. Now, if I use the exponential function, the probability that Tsn is greater than nt is equal to the probability that exponential Tsn is greater than exponential nt. So now I am in the position where I can use Markov inequality. I will use Markov inequality with capital X being equal to exponential Tsn and A being equal to exponential nt. So I go back to Markov inequality. Here, my X will be exponential Tsn and my A will be exponential nt. So from Markov inequality, the probability that my binomial random variable is smaller than n, this probability is less than exponential nt times the Laplace transform of my binomial random variable. So now the idea is to compute the Laplace transform and then to make an optimization over all possible values of t. You follow me well? Is it okay?
Yes, sir.
So
Yes, sir.
we will do it now.
Sir,
Yes?
sir, there is can, can you please reverse the slide, the previous one,
Yes?
where you have asked that we can't use Markov equality here?
Yes. What is
Yes,
your
sir.
question?
In this case, someone gave. Sir, I mean, sir, here told that we can't use Markov inequality here since the equality signs is in opposite direction. Why can't we use this probability as n minus probability Sn greater is equal to n? And then in terms of at this where inequality is in the same direction as required Markov inequality, we are using this term. Are you getting my point?
I think perhaps the key point is that I'm using a negative value of t, a negative value of t. So I can reverse the sign of my inequality. And this is the point. If I use a negative value of t, all is okay. If I use a positive value of t, all will be not okay. So if I assume that t is negative, it will work.
Yes, sir. This I have got it. I'm saying the place at the point where this question arises that we can't use the Markov inequality just inequalities in opposite direction as required by Markov equality. So point, it is required that probability Sn is less than greater than n. So that our expression is in the form that probability Sn less than is equal to n. Can't we write this like 1 minus probability
No.
Sn
No.
greater than n, and
No,
then
no.
Markov equality?
No.
Yes.
No.
So why it is so? This is my answer.
Your idea is to if I follow you well, your idea is to write that the probability that Sn is smaller than n is 1 minus the probability that Sn is greater than n. But how you will manage with the probability that Sn is greater than n? You will find an upper bound using Markov inequality. But here, it's 1 minus the probability that Sn is greater than n. So if you obtain an upper bound for the probability that Sn is greater than n, because of the 1 minus, because of the minus sign, it will not work. If you have an upper bound, not a lower bound, no, if you have an upper bound, it will not work. If you have a lower bound, it can work, but it's very difficult to have a lower bound. Okay? I repeat myself, the probability that Sn is smaller than n is 1 minus the probability that Sn is greater than n. So because of the minus sign, if you follow that direction, you will have to prove a lower bound for the probability that Sn is greater than n. And it's difficult to prove lower bounds. And with Markov inequality, it will not work, because with Markov inequality, you have an upper bound, not a lower bound. Okay? So let's continue.
Sir.
So let's continue. Now we have to compute the Laplace transform of my binomial random variable Sn. So I'm sure you know that a binomial random variable can be expressed as a sum of independent random variables sharing the same Bernoulli distribution. And the parameter for the Bernoulli or for the binomial is a half. So let's do it. Sn, I can write Sn as a sum from 1 to capital N of xk. And the xk are independent with Bernoulli distribution. So I'm able to compute the Laplace transform of Sn. So the Laplace transform of Sn is the mean value of the exponential of t sum from 1 to capital N of xk. Exponential of a sum is a product of exponential. And now, as the random variables are independent, the mean value of a product is a product of the mean. The mean of a product is a product of the mean because they are independent. And now it is only necessary to compute the Laplace transform of all my random variable xk. But xk takes two values. The value 1 with probability 1 over 2, and the value 0 with probability 1 over 2. So exponential, the mean value, the Laplace transform of my Bernoulli distribution is 1/2 exponential 1 plus 1/2 exponential 0. So it's 1 plus exponential t divided by 2. And all the Laplace transform of my random variable are the same. So I can say that it's 1 plus exponential t/2 at the power capital N. So now I obtain that the probability that Sn is smaller than n is less than exponential n times phi t, where phi t is t minus capital N/n, the logarithm of 1/1 plus exponential t divided by 2. I go back because I want you to follow me well. What exponential nt is here. So exponential n times t is here. And the second term, I just say that the Laplace transform of Sn is the exponential of the log of the Laplace transform, exponential of the log. So the capital N can be dropped here. And so the capital N is here, and the N is here because I multiply by N, and the minus sign here. So I have to put a minus sign here. So now we will use the idea of Chernoff. The idea it was given in a paper of Chernoff in 1952. Because the idea is the following: the left-hand side does not depend on t. The right-hand side is depending on t. So I can't make an optimization and compute the value of t such that the right-hand side is as small as possible. So because of the minus sign here, I can compute the value of t such that phi of t is the largest possible. So this is the idea of Chernoff, and this idea is widely used in concentration inequalities. So let's look at the value of my function phi t. So I can compute the first and second derivative. If I compute the first derivative, the derivative of t is 1, and the derivative of the logarithm here is simply exponential t divided by 1 plus exponential t. The second derivative is very simple also, and what can we see now? We can see that the second derivative is always negative, which means that my function phi is concave. And so it reaches its maximum where the first derivative is 0. So I have to find the value of t such that phi prime of t is 0. Phi prime of t is 0 if and only if 1 is n exponential t divided by small n times 1 plus exponential t. So phi prime of t is 0 if and only if n times 1 plus exponential t is equal to capital N exponential t. So it is easy to compute the optimal value of t, and the optimal value is given by the logarithm of n divided by capital N minus t. An important point here is to check that the optimal value is negative, because I start with a negative real number t. So the t star is negative if and only if my n divided by capital N minus n is smaller than 1. And n divided by capital N minus n is smaller than 1 if and only if 2 times n is smaller than capital N. Okay? Do you follow me well?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So here, in this example, you see many things, because you see the idea of Chernoff, which was used by many researchers in that domain, for example, by Hovding, by many people. So compute the optimal value, because on the left-hand side, the probability does not depend on t, while on the right-hand side, the function depends on t. So if you are able to compute the optimal value such that the right-hand side is the smallest possible, you will have a good concentration inequality. Okay, let's continue the computation. So what I am doing now, I plug the optimal value t star in exponential n phi t. So I plug the optimal value t star here. So I replace my t by t star. So the first quantity is n times t star, and the second quantity, I just replaced my t star in the log of 1 plus exponential t divided by 2. I just plug my t star here, and the computation is very easy. So log of minus n, exponential minus n log of a quantity is the 1 over the quantity at the power m. So the first term here is easy. Here you can see a 2 log of a over b is log of a minus log of b. So you will have a n time minus n time log 2. So exponential minus n log 2 is simply 1 over 2 to the power n. Okay. And now what I am doing, I am replacing, I am plugging a capital N at the power n here. And so my term, my remainder, Rn, is simply n minus n over n at the power n minus capital N. So I have to find a nice upper bound for my remainder Rn. So capital N minus n over capital N is 1 minus n over capital N. So my x here will be small n over capital N. Small n over capital N is always smaller than 1. So thanks to this elementary inequality here, and you can check very easily that this inequality is true, you find a nice upper bound for Rn. And a nice upper bound is exponential n. This upper bound does not depend on capital N. So thanks to this upper bound, I can go back to my problem and say that exponential minus n times phi of t star is smaller than 1 over 2 to the power n exponential 1 times capital N over n at the power n. So as my sum is 2 to the power n times my probability, the 2 to the power n are cancelled, and I solve my problem. Is it okay for everyone?
Yes, sir.
Yes, sir.
Very good. So in this simple example, you see many things. So this is why I have chosen to start with this simple example. So I will continue with a second motivation. My second motivation is a statistical application. I want to compute exact confidence intervals, not asymptotic, but exact. Because imagine you have a sample with small values of n. If you have a sample with n very small, you cannot use asymptotic result to obtain exact confidence interval. So my goal here is to obtain exact confidence interval for my parameter P here. So I have x1, xn independent random variables sharing the same probability distribution, the Bernoulli distribution with parameter P. And I want to compute an exact confidence interval for P. So the empirical mean x bar n converges almost surely to P. I also have a central limit theorem. So x bar n is what we call in statistics an unbiased estimator of P. It's a good estimator of P. So my goal is to compute exact confidence interval using the empirical mean. Okay, so let's do it. A first naive approach is to make use of Markov inequalities, because the probability that the absolute value of the empirical mean minus P greater than A is the probability, you can put a square here, that x bar n minus P at the power 2 is greater than A at the power 2. So is 1 divided by A at the power 2, the mean value of x bar n minus P square, so the variance of x bar n. And we saw before that the variance of x bar n is P1 minus P divided by n. So we obtain P1 minus P divided by N times A squared. So as P is between 0 and 1, for P1 minus P smaller than 1. So this quantity is smaller than 1 over 4 times N A squared. So the reverse inequality is greater than 1 minus 1 over 4 N A squared. So if I denote by alpha 1 over 4 N A squared, the alpha will be between 0 and 1 as soon as N is large enough. Large enough means that N is greater than 1 over 4A squared. And then, thanks to Markov inequality, I obtain a first confidence interval. A first confidence interval for P is given by x bar n minus this. So what I am doing here, I just solve the expression alpha is 1 over 4 A squared. So 1 over 4. Here you have 1 minus alpha. So now I just have to say what is the value of A. The A squared is 1 over 4n alpha. So A is 1 over the square root of 4n alpha, and the square root of 4n alpha is 2 square root of n alpha. So to compute an exact confidence interval using Markov inequality is very easy. But you will see later that this confidence interval is very large. So our idea is to use concentration inequalities to obtain a better confidence interval for P. Okay, what about the asymptotic confidence intervals? So if I use the central limit theorem, I will obtain this asymptotic confidence interval, which is true if n is large enough, and where A here is the quantile of the normal distribution. The quantile of order 1 minus alpha divided by 2 of the normal distribution. But I just want to say that this result is true for n large enough. And if you have a small n, it's impossible to use this central limit theorem. I can use Slutsky theorem also. The idea is to replace in the central limit theorem here square root of P times 1 minus P by the square root of the empirical mean times 1 minus the empirical mean. So here you have the square root of the empirical mean 1 minus the empirical mean, and it will change a little the asymptotic confidence interval for P. But as before, this asymptotic confidence interval is true for n large enough. Finally, and this will be the purpose of in 10 minutes, you will see what is of the inequality. But thanks to Hofding inequality, you can prove this nice exponential bond here. And you can compute this exponential bond very easily. So you will obtain a good exact confidence interval using Hofding inequality. And the confidence interval is given by x bar n minus the square root of this. It is exactly the same computation as the previous one with Markov inequality. In the previous one with Markov inequality, I just have to say that alpha is 1/4 n a squared. So I just have to compute the value of a, and the value of a gives you this bond 1/2 times the square root of n alpha. And I do the same thing here. Alpha is 2 exponential minus 2n a squared. So a is the square root of the logarithm of 2/alpha divided by 2n. So I obtain this exact confidence interval using Markov inequality. So let's look at this picture. The red line here is given by the Markov inequality. To better explain this figure, I just compute the values here, So you have minus plus a quantity. And if this quantity is very small, my confidence interval will be better. So in red, you have for n varying from 10 to 100, you have I have plot this 1/2 square root of n alpha. Okay. In blue, you have the confidence interval given by Hofding inequality. And the confidence interval given by Hofding inequality is always better than the one given by Markov inequality. And those lines are the asymptotic confidence interval given by the central limit theorem and by Slutsky theorem. We can see here that they are, of course, better than the exact confidence interval given by Markov or Hofding inequalities. But they are only true for n large enough. So you can have situations where it is impossible to make use of asymptotic confidence interval because the values of n are too small. Okay. Is it okay for everybody?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
good. So now,
Sir,
yes?
what is the interval, confidence interval, which is more shrink, like I think interval k. What is the interval k? Based on Markov inequality, or it is based on Holder inequality?
I think I don't
Hofding
understand.
inequality.
I don't understand your question.
Sir, I want to ask that what is the interval interval k, like the
K.
smallest.
The interval k is given by Slutsky theorem.
Okay.
It's the one given by Slutsky theorem. This one.
Sir, so Slutsky's theorem gives us more compact confidence interval than any other confidence intervals.
Can you repeat your question?
Yes, sir, I am saying that the Slatsky's theorem gives us more compact confidence interval rather than any other approach by using Markov or any other approaches.
In this situation, in this particular case, Slutsky theorem is, it depends on the value of n. For n in this zone, for n being 40 or 50, Slutsky theorem or the central limit theorem are more or less the same. For small values of n, Slutsky is better. The confidence interval is more compact. But in this example, you can see that those confidence intervals are better than the exact confidence interval. But in theory, you cannot use them. For n, if n is 20, I cannot use the central limit theorem to derive a confidence interval because n is too small. So in reality, it's impossible to use the central limit theorem or Slutsky theorem to deduce confidence interval. So, okay. So
Okay,
now we will continue with the theoretical part of my talk. This was an introduction and motivation. So Vasily Hovding was a Finnish statistician and probabilist. He finished his career in in Princeton University, I think, in the USA. He has written only 38 papers, only less than 40 papers, but is very, very well known. And many recent papers in GMLR or in statistical learning, deep learning, etc., they use Hovding inequality. So he makes a lot with very few papers in this area of probability. So the Hovding inequality is very simple, but it only works for bounded random variable. So imagine that x1, xn are finite, is a finite sequence of independent random variable, and I denote by Sn the sum from 1 to n of xk. And a very restrictive assumption, but in the binomial case, it works. Because in the binomial case, is my random variable are between 0 and 1. So if I assume that my random variable are bounded by AK and BK, I obtain that the probability that Sn minus the mean value of Sn is greater than x, or the absolute value, you put a 2 here, is the probability that Sn minus the mean of Sn is greater than x is always smaller than exponential 2x squared divided by dn. Okay, so for example, imagine that all the AK are 0, all the BK are 1. So the previous situation of Bernoulli random variables. My dn will be what? If all the AK are 0, all the BK are 1, what? My dn, what is the value of dn? This is a question. N, exact. My value of dn will be n. So this is why here you have n here. I better explain myself. The probability that Sn minus the mean of Sn greater than x in this situation will be 2 exponential minus 2x squared divided by n. So if I'm more interested about the empirical mean, I have to divide Sn by n. If I divide Sn by n, the mean value of Sn over n, the mean value of Sn over n will be the mean value of x bar n will be p. So if I want to use Markov Hofding inequality, I have to divide this quantity by n. So I have to divide x by n. So probability that x bar n minus p greater than x over n is this. So probability that x bar n minus p greater than z, for example, I have to replace x over n by z. So if I denote z to be x over n, x will be z times n. X will be z times n. So, here it's a. Sorry. So I replace x over n by a. A is x over n. So x is n times a. N times a. So here I will have minus 2 at the power n times a square divided by n. N times a square divided by n will be what? N times a square divided by n. Finally, you will have what? This is a question. I denote a to be x over n. I denote a here to be x over n. If a is x over n, x is n times a. So at the right-hand side, you will have minus 2 times n times a square divided by n. N times a square divided by n is n square, a square divided by n. So finally, it's n a square divided by nothing. So you will have minus 2 n a square, minus 2 n a square, minus 2 n a square. Do you follow me well?
Yes, sir.
Yes, sir.
Okay, so thanks to Hofding inequality, you immediately obtain in the Bernoulli case, you immediately obtain this inequality. So this inequality will be given by this more general result. So how to prove it? We will prove it now. So the proof relies on the convexity of the exponential function. In blue here, you have the exponential function. Here I have a value A, a value B, and if I put a line between A and B here, the line will be always greater than the blue curve. So if I denote X a value between A and B, because here I assume that my xk are between A and B. So if I put a value X between A and B, exponential X will be always smaller than the point here given by the line passing from this point to this point. Is it okay for everybody? Is it okay?
Sir, can you please repeat this?
The blue curve is the exponential function, the blue curve. If I choose 2 points, A and B, here A is 5, B is 8. If I choose 2 points, and if I draw a line passing from these 2 points here, the line will be always greater than the blue curve, which means that if I pick a point X between A and B, exponential X will be always smaller than Cx plus D, where C and D are given by these 2 points. You have a line passing from these 2 points, so it's very easy to compute C and D. And then exponential X will be always smaller than Cx plus D. This is the idea of the inequality. So let's continue. If I have a random variable X such that X is greater than A and smaller than B, I can prove that the Laplace transform of my random variable is always smaller than exponential t squared over 8 times b minus a squared. And to prove this lemma, we use the convexity of the convex function. This is exponential tx. I said before that exponential x is always smaller than cx plus d. So my blue curve will be exponential tx. My blue curve will be exponential tx. This is the c and this is the d. Exponential tx is always smaller than cx plus d. The c is exponential tb minus exponential ta over b minus a, and the d is this quantity. Just the convexity of the exponential function. Is it okay for everybody?
Yes, sir.
Yes, sir.
So now I put the expectation on both sides. If I put the expectations on the left-hand side, I will have the Laplace transform of my random variable x. Now, if I put the expectation on the right-hand side, this is a deterministic quantity c. This is my random variable x, and this is a deterministic quantity d. If I assume that my random variable has 0 mean, my random variable is 0 mean, if I put the expectation on the right-hand side, the mean value of cx plus d is c times the mean of x plus d. the mean of x is 0. So this quantity vanishes. And it will only remain the d, and the d is this quantity. Now the idea is to replace the d by 1 minus p exponential py plus p exponential 1 minus py, where p is, sorry, where p is 1 minus a divided by b minus a. You can see p here, minus a divided by b minus a, and y is b minus a times t. So if I denote by hy the function minus py plus the logarithm of 1 minus p plus p exponential y, the Laplace transform of my random variable is always smaller than exponential hy. Okay, this is given by the previous slide here. So now I have to find an upper bound for my function h. If I compute the first derivative, the derivative of minus py is minus p, and the same calculation as in the first illustrative example. I compute the first derivative, the second derivative, and what can I see here is that the second derivative is always smaller than 1/4. So thanks to Taylor's formula, hy, it's h0 is 0, plus y, h prime of 0, but the h prime of 0 is 0, plus y squared divided by 2, h prime of z, h second of z, h second of a quantity. But the second derivative is always smaller than 1/4. So you will have y squared divided by 2 times 1/4. So you will have y squared divided by 8. And y, if I go back, y is simply b minus a times t. So y squared is b minus a squared times t squared. So you have this t squared over 8 times b minus a squared. So if I use the exponential, I finally obtain this upper bound. The upper bound here. Okay, I think I have to stop because time is over. So do you have questions?
Sir,
Yes?
in the previous slide, I can't get y e to the power tx less than equal to e to the power tb. Yes, this one, sir. I can't. Why this is come from the convexity?
Okay, you don't understand this blue line here. This is your question.
Yes.
Okay, imagine that the blue curve is exponential tx, exponential tx. So here, if I choose a x between A and B, you will have exponential tx here. Exponential tx is always smaller than cx plus d. Exponential tx is always smaller than cx plus d, and the c is given by this, and the d
is B.
given.
Okay, sir. Now.
You just have to write. If you have 2 points, you can put a line between those 2 points. So it's very easy to compute C and D. It's a easy calculation. C is given by here and D is given by here.
I'm just putting the two values of C and D and getting the inequality.
Yes, exact.
Okay. Thank you, sir.
You're welcome. Do you have other questions?
Sir, am I audible?
Yes.
Sir, I could not understand how we arrived at the expression of hy.
Can you repeat your question, please?
Sir, I could not understand how we got to the expression of hy. How we got that? How did we get that?
Hy. Hy. Okay. It's not complicated. You want to know how you obtain this expression. Okay. Okay. Okay, I understand. Here, you have 1 minus p exponential minus py. So it's exponential minus py plus minus p exponential minus py. So what I am doing here, I make a factorization. I make a factorization with exponential minus py, and then I take the logarithm. If I make the factorization and then use the logarithm, you will have exponential minus py here, and then you will have the remainder term here. I just make a factorization. Sorry, I just make a factorization with exponential py. It will be 1 plus a quantity, and then I compute the logarithm of this. Is it okay?
Yeah, okay, sir. I got it.
Okay. Other questions?
Hello, sir.
Yes?
Is it possible to get the slides?
To get, yes, of course. I will send you the slides. I will reply to your questions this afternoon, and I will send you the slides at the end of the afternoon.
Thank you, sir. Can you suggest us some more reference books on this subject?
I put my book in reference, so you can have a look to my book.
Okay, sir. Thank you.
This one, you can find it in the web easily without paying charges. It's very easy to find it in the web.
Okay, sir. Thank you.
You're welcome. So tomorrow we will continue the proof, and we will see how to improve Hoeffding inequality. And then we will finish by Kramer-Chernoff calculations example of Kramer-Chernoff calculations, and I will give you some open problems if people are interested to work on in this area. Okay?
Okay, sir.
Okay, sir.